So, welcome again to the new lecture of the course Properties of Materials. So, let us just briefly recap what we did in the last lecture. So, in the last lecture we basically introduced the topic of dislocations. So, we just mentioned that dislocations are the ones which contribute towards lowering of strength, okay. And then we just briefly started looking at dislocations. Dislocations are of two types, edge and screw dislocations, and we were looking at their characteristics. So, just for the ease of visual appreciation, I am going to show you a PPT in this lecture. So, just we already had the discussion in the last lecture. So, we will just go through briefly about it. So, this is what dislocations basically are. So, a dislocation, if you look at the perfect crystal, this is what it is. So, if you start from P, you go to M, M and O. If you start from M, you go to N, you go to O, you go to P, you go to M, back again by taking. So, number of steps up and down and number of steps left and right are similar, and you reach the same location by going up and down and left and right. But if it is an imperfect crystal, supposing you have this extra row of atoms here. So, this is an extra row of atom, okay. Then when you go from M to N and N to O and O to P and then again P, if you want to go back from P to M, you have to take this extra step, because the number of steps that you took from N to O is equal to from number of steps from P to Q. So, from going to Q to M, you have to take this extra step, and this extra step is Burgess vector. And so, this is what is the edge dislocation, but you can also have a screw dislocation in which you shear one half of the crystal with respect to another half of the crystal by applying shear stress. So, when you apply shear stress in this direction, this part of the crystal shears, and this line which runs through the crystal in this fashion, this line marks the separation between, this is the sheared part, and underneath this is the unsheared part. So, if you keep applying the stress, this line will move in this direction, making the whole crystal sheared after a while. So, this is what a screw dislocation will do. So, this is a edge dislocation and this is a screw dislocation. And so, this is a perfect crystal that so this is what we defined. So, you have this extra row of atoms. In the otherwise perfect crystal, you have this extra row of atoms which has been put, and this extra row of atoms is going to move in this direction or in other direction, and the extra step that we created Burgess vector B, and the plane on which this extra row of extra plane of atoms will move can be visualized in this fashion. So, you have a slip plane. In the slip plane, this extra half plane will move either to the left or the right depending upon the stress, and the line adjoining this extra half plane and the slip plane is the slip line. So, this blue one is the the dislocation line, and this dislocation line has a certain relation with respect to Burgess vector. So, it is perpendicular to applied, so this is the applied stress tau. So, you can see that Burgess vector is parallel to applied stress, and both Burgess vectors and applied stress are perpendicular to the dislocation line, and the dislocation line moves in the direction of applied stress. This is for the edge dislocation. This is the screw dislocation. So, by the way, all these slides have been taken from Professor Anand Subramaniam, who has made very nice illustrations. They are available online as well. So, this is the illustration of the screw dislocation. So, this is a Burgess circuit that we draw. So, when we go from A to B, B to C, C to D and D to A. So, A to D should have been equal to B to C, but there is an extra step that is created in between, which is this Burgess vector. So, here the dislocation line is perpendicular to this ABCD. So, that is, it runs across the crystal in this fashion. So, this is your T, and so here the Burgess vector is parallel to the dislocation line, and the stress that you apply is in this direction. Okay. So, this is the stress direction. So, when you apply stress in this direction, as you apply the stress, let me just change the color. The dislocation line is going to move to this direction. So, this is the motion direction, direction of, let us say, motion of T. Okay. So, T moves perpendicular to the applied stress, and as a result this motion is also perpendicular to the Burgess vector. So, when you keep moving it, it will become into a perfect crystal and you create a step. In reality what happens is that we have a dislocation which could be something like this in the form of a loop, or it could be in this form, in which on one side if you look at the crystal it looks like a screw dislocation. So, this is the screw component because the Burgess vector is parallel to the slip line, but here if you look at this part of the crystal, this is the edge part. So, this is the extra row or extra plane, and here you can see that the Burgess vector is in this direction and this is T is in this direction. So, here T is perpendicular to B and here T is parallel to B. So, as a result you can see there is a loop there, you can have this in the form of a loop. So, if this is the overall Burgess vector that you have, wherever you have B parallel to T, that will make a screw dislocation, and wherever you have and the screw dislocation is depicted by these screws. So, this is the right hand screw, this is the left hand screw, or you can say this is the clockwise, this is the anti-clockwise, and so this is negative generally screw dislocation, this is positive screw dislocation. So, you can see that this is edge, this is edge because B is perpendicular to T, and here so this is T. Okay. This is also T. So, dislocation line is T, and wherever B is parallel to T, it is screw. So, these two are screw, and wherever they are not, this would be mixed. So, mixed, this, that and that, all of these will be mixed dislocation. So, how does a dislocation move? Basically, the motion of a dislocation leading to formation of a step. So, let us say you have this extra row of atoms here, you go from here to here, when you apply shear stress, so this extra row moves to the next one. So, which means this row goes in this fashion, this will come forward. So, it moves to position. So, this is position 1, position 2, then it moves to, let us say, position, I do not know, maybe 3. It goes to position 4, which is the step. So, it creates a characteristic step that you, so it comes to this position 4 and then it goes to position 5. So, it goes in this fashion, creating a surface step. So, basically what happens here is when the dislocation moves, initially it had bonds with these two atoms, then it creates bond with these two atoms, then it will create bonds with these and these. So, essentially what it does is that it needs to break bonds with one of the atom. Okay. So, basically this atom, these bonds locally will get reorganized when the extra half plane appears to be moving. So, it is not the whole plane actually which is moving, it is just that local reorganization of few atoms. So, this group of atoms is essentially getting reorganized as you keep applying the stress. So, this you can say this zone keeps moving forward. So, it is not the whole bunch of atoms which are moving, it is just this bunch of, it is just this local group of atoms which are moving forward to make it look as if the whole plane of atoms is moving, giving rise to finally the formation of a step. So, this is what you create. So, it is this local bunch of atoms which reorganize themselves when the shear stress is applied, not the whole lot of atoms, and that is why the stress is lower, and this leads to, so note that locally bonds get reorganized when a dislocation moves, the extra half plane does not move as a whole, and this is what leads to lowering of stress, because you are not moving all the atoms with respect to all other atoms, you are moving just a local group of a few atoms to make this happen. Similarly, screw dislocation, if you have a screw dislocation like this is the perfect crystal, this is the screw dislocation, and as you keep applying the stress in this direction, this dislocation line moves in this direction, the step gets created across the whole crystal. When you come here, finally you have this extra step B. So, this is the screw dislocation, again giving rise to to the creation of a step. So, these dislocations together they give rise to what we call as formation of step, which is similar to what we see in slip. So, the formation of steps is very similar to the kind of steps that we form in via motion of dislocations. So, just to summarize now the dislocation characteristics. For edge dislocation, Burgess vector is perpendicular to dislocation line. The slip direction is parallel to Burgess vector, and the direction of dislocation line motion with respect to Burgess vector. So, the dislocation line moves parallel to the Burgess vector. For a screw dislocation, the Burgess vector is parallel to line, the slip direction is parallel to Burgess vector. Slip direction is parallel to Burgess vector in both the cases, whereas the dislocation line moves perpendicular to the Burgess vector in case of screw dislocations. These are some fundamental differences that you can, and you can also write like the stress. Okay. So, stress. So, in case of edge dislocation, tau is parallel to B, and here also tau is parallel to B, but here tau is perpendicular to T, here tau is parallel to T. So, you can write these relations as well. So, these are all related, dependent upon each other. If you work out some of them, you will work out naturally the other ones. And then if you look at the Burgess vectors so Burgess vector is basically along the slip direction. So, slip direction is the direction which is the close pack direction. So, Burgess vector in cubic crystals are defined, for example, if you take monatomic FCC, the 110 direction is the close pack direction. So, if you look at FCC, the face of FCC is this. So, this is FCC, and this is the 110 direction. Okay. So, this is 100 plane of FCC, this is the 110 direction. So, the Burgess vector is from this atom to this atom. So, this is the B. So, B is half 110. Okay. Similarly, in case of BCC, so let me just go to the, in case of BCC, this is half 11. In case of monatomic simple cubic, it is 100, and the moment you have ionic solids, it changes to half 110 and 100, because you need to move an atom from, you need to move, let us say if you have A atom, you can only move to the another A atom, you can't move from A to B. A to B is not a Burgess vector, A to A is the Burgess vector. Shortest distance that you require to move A to A position is the Burgess vector. So, let me just go through a little bit in the next one. So, this is for example the BCC, and you have one extra atom in the center. So, assuming that all of them touch each other, the close pack direction is the direction which is this direction. So, close pack direction touches this, this and this. So, this is your, you can say 111 direction for BCC. Okay. Let me use a different color maybe. So, this is the close pack direction. From A, it goes to central atom B, it goes to the corner atom C. So, half of, so Burgess vector will be half of AC, and this is half of 111. This is the Burgess vector in BCC, that is what we said. So, it goes from one atom to the next nearest neighbor. So, A to B, or you can say is equivalent to AB. If you take FCC, or let us take simple cubic first. So, this is simple cubic, let us say this is the atom, these are all touch each other. Okay. So, when they are touching each other, then the closest direction is the cubic direction, which is from here to here. So, this is what is the B, and this will be equal to 1 0 0. Okay. If you look at FCC, you have one here. I cannot draw it's difficult to draw structure with touching atoms. So, let us not make the touching atoms. There is one here, one here, one here, one here, one there and one here. All these atoms within a plane touch each other. So, let us say the close pack direction is, this is the close pack direction. So, this is the closed packed direction. This will be on one of the planes, let us say. So, you can also see visualize the plane. So, this would be on this plane, okay. This will be the slip plane, the plane in which dislocation will move. In this case, the plane will be, of course, this plane. In this case, the plane will be this plane, 1 1 1 type of plane. So, this direction will be half of, oops. So, this direction will be half of 1 1 0, that is Burgess vector for a FCC. This is simple cubic. Now, and if you take a cesium chloride, for example, crystal, if you take a cesium chloride crystal or copper zinc system, in copper zinc, let us say if you have this kind of copper zinc where this is copper and then you have zinc somewhere in between. So, this is zinc. So, this is zinc and these are all copper. Now, if you want to determine the Burgess vector will be, so this will not be Burgess vector. You can go from copper to zinc, but you are not going from, so this is not B, B will be this. So, this will be B. So, although it looks like BCC, it is a simple cubic lattice. So, to go from one copper to copper, to go from one zinc to zinc, you have to move in 1 0 0 direction. So, that is why in the previous slide we said for cesium chloride kind of structures it is 1 0 0. For sodium chloride it is FCC structure, again to go from, so if this is sodium chloride, this will be chlorine atom and sodiums will be sitting, so if sodium chloride, sodiums will be sitting here, and again to go from one chlorine to another chlorine you just need to follow the same direction. So, this is for both FCC as well as NaCl, and diamond cubic will have direction, again the diamond cubic is again FCC kind of structure. So, you again need to follow the 1 1 0 type of, half 1 1 0 type of vector. So, these are the directions which you need to follow for Burgess vectors in crystals. So, this gives you a fairly good idea about what dislocations characteristics are in crystals. So, let us just, so we have basically discussed what dislocations are, and if you wanted to follow more details then you need to go to the course structure of materials to know more. Okay, so what we have done is basically till now we have looked at edge dislocation and screw and how to define the Burgess vectors in crystals, especially cubic crystal. Okay. Now, what we do is that we also see how do they move in the crystals. Now, how do you examine dislocations in a given material? There are various ways of examining. So, basically dislocations can be examined by basically what I mean is that how do you see whether you have dislocations in the crystals? You can see them by a technique called as edge pitting. So, essentially you use a etchant, and dislocation being a high energy or high stress area gets etched preferentially as compared to, so basically you see etch pits. So, So, Hnt is basically sort of an acidic solution, and this acidic solution is applied to the crystal in a very controlled manner, and the places where you have dislocations which terminate on the surface, they get etched more than the other regions. So, basically you start seeing them as these kind of pits. So, these could be the dark pits which are visible in the microscope in the crystals. You can also see them using transmission electron microscope. So, basically they show what we call as dislocation contrast, all right. And so you can see them dislocation, you can also see dislocation motion in TEM. So, these are very specialized topics, I am not going to go into details of these, but basically this is how they are going to move. Now, how does, so having known this about the dislocations, now the next question is how do you translate this information about dislocation motion into slip phenomena. So, for that I am again going to take help of another PPT to show you illustrate the principle of. So, basically what I have here is, so let us say on the left we have a perfect part of the crystal, this is the perfect crystal. In this crystal, if you look at on the left, I create a dislocation. So, this is a dislocation that we create, okay. So, this dislocation is basically done by pushing an extra row of atoms. So, we basically push an extra row of atoms from the neighbor. So, push, and you can't bring atoms from anywhere. So, it has to come from somewhere, it comes from within the crystal itself. So, push an extra row of atoms. So, dislocation will form when you apply stress. When you applied stress, so these are various let us say stacks of planes, okay. So, what happens is that when you apply stress, this dislocation will move out and it will create a step in this direction. When you apply further stress, you create another dislocation in this manner. So, this is another dislocation that is created. This will push the next plane to move out of the crystal in this fashion. So, you created first step here. So, the first step is here. Now, this is the second step. This is the first one. This is the second step that you create. So, if you keep doing that, so you had the first one, you have the second one, and then you create the third one, and then you go 1, 2, 3, 4. So, you keep creating the steps, and when you look at it on a macroscopic scale, this is how it will look. This was the red dots or red dashes show the original crystal, which was a square crystal, and by the motion of dislocation in successive planes, it has given rise to a sort of parallelogram. So, the crystal has become from a rectangular crystal to it has taken a different shape in this form, and this is what basically is the deformation. You have gone from this shape to this shape, and this is what has happened with the, and each of these step, by the way, is equal to nothing but Burgess vector. So, this is Burgess vector. So, multiple Burgess vectors you create on the surface, and that is why when you look at the slipped crystal, the slipped crystals will look something like this. If you look at them under the microscope, they will show you these steps on the surface. So, this is how it will create the steps on the surface and to look like a deformed body. So, this is how it is going to look like. So, a perfect crystal when deformed by motion of dislocation in the successive plane, it leads to creation of these steps, and you can see that it creates a deformation. What happens here basically is there is no change in the volume. Volume remains constant. So, the constancy of volume has to be followed. There is no change in crystal structure, which means the crystal structure of the material does not change. So, the volume does not change, the crystal structure does not change, you only obtain what we call as shape change, and this shape change is permanent, and this is what is basically we can say is plastic deformation. Okay. And so, essentially what we are saying, just to summarize, we say, so just to summarize, we say plastic deformation happens by slip, and the slip takes place by motion of dislocations, because theoretical strength for slip is very large, that is not practical. Experimentally observed values are much lower, and they happen by the presence of these defects called as dislocations. So, basically dislocations move on slip planes along slip directions, which are also defined as Burgers vector. This motion requires much lesser stresses than required in a perfect crystal, and that is why real crystals are softer. Okay. So, basically the real crystals will have these, let me just again reiterate this point before we. So, when you move this extra row of atoms, it is not the whole plane that moves, it is only this group of atoms where the bond reorganization occurs only in the vicinity of dislocation line, not in the whole plane. So, although it looks as if the whole plane is moving, it is just that line which moves, just that core which moves. So, only a bunch of atoms require. In a perfect crystal, on the other hand, if you had a perfect crystal like this, in the perfect crystal all these atoms move. So, this is perfect and this is real. So, that is why tau perfect is larger than tau, much larger than tau real, and this is due to dislocations. So, I hope it is clear that why the stress required to move dislocations is smaller in real crystals which consist of dislocation than in perfect materials. We have initiated this part actually, the plastic deformation. We have introduced the concept of dislocation. We have also shown that why the stress required to stress required to deform a real crystal is lower than the perfect crystal. We will do more detailed discussion on this in the next few lectures. Thank you.